Welcome back everyone. In this lesson we are going to learn about another open method which is known as Newton-Raphson method, one of the most widely used open methods to find the roots of equations. In the last lesson we learned about incremental search method, and also later we learned about another open method which is termed as simple fixed point iteration. So simple fixed point iteration is our very first open method that we would like to apply, but there are other advanced methods like Newton-Raphson method and other methods that we are going to cover in our this lesson and later lessons. So let's look at what Newton-Raphson method is. So as we already said, the Newton-Raphson method is an open method. That means, unlike the bracketing methods, the open methods require a single starting point. We already have known that about this issue in our simple fixed point iteration approach. But since also Newton-Raphson method is an open method, we require a single starting point. Okay. So look at this figure. In this figure, the function is given, which is this curve. The function is given at this curve by this curve f of x. And what we do, initially we approximate a value xi. We plot a tangent curve to the function at the corresponding function value of xi. That means xi is our initial point. We draw a tangent curve to the function at the f of xi point. That tangent point is going to intersect the x-axis at another point, that means xi plus 1, and this xi plus 1 is our new approximation of the root. So that is the main theme of Newton-Raphson method. That means we draw the tangent curve at a function at a value, and we calculate the point at which that tangent curve is going to intersect the x-axis, and that intersection point is our new approximation of the root. So how do we mathematically formulate this Newton-Raphson method? First, we initially specify an initial point, that means our initial assumption xi. We find out that there is a triangular shape that is formed with within this area. That means with the tangent of the curve and the base of the line, which is x-axis, which is xi, situated between the xi and xi plus 1, and this is the height. This is the height f of xi minus 0, and this is the base xi minus xi plus 1. So we can form a triangle within this area. So what we are going to do, we are going to find out the slope of this tangent curve at this point. That means f prime of xi at xi point. So what is the slope of the curve, which is the height divided by base, and the height is f of xi minus 0, and the base is xi minus xi plus 1. So if we reformulate and rearrange this function, we get xi plus 1 equal to xi minus f of xi divided by f prime of xi. So equation 1 is our basic Newton-Raphson formula. With this formula, we can find out the new approximation of the root using the previous approximation. What is the previous approximation? Xi is our previous approximation, and xi plus 1 is our new approximation. So this is the basic Newton-Raphson method that we are going to use whenever we apply this formula. So this is our Newton-Raphson formula. Look at this. We require the previous approximation xi. Also we require the function values f of xi and its derivative at xi. So f of xi and f prime of xi, that is the derivative of the function, both can be determined using the forward dividend difference formula. If you remember from lesson 4, look at this, xi minus f of xi divided by f prime of xi. Now, in this case, we need to determine the f prime of xi, which is crucial for Newton-Raphson formula. So how do we calculate this f prime of xi? This is the bottleneck. So we can calculate numerically using the finite dividend difference formulas. If you can remember from lesson 4, we used forward dividend difference formula, backward dividend difference formula, and also central dividend difference formula there. So using any of these formulas, we can determine the derivative of these functions. So once we determine the derivative of the function, we can use equation 1 to find out our next approximation of the root using Newton-Raphson formula. So let's look at the algorithm that we are going to use for this method. In step 1, we are going to initially guess a root, that means our initial assumption xi, and once we get the xi, we will approximate our new root xi plus 1 using the Newton-Raphson formula. Then this xi plus 1 equal to xi minus f of xi divided by f prime of xi. So whenever calculating this formula, we are going to use the finite divided difference equations from lesson 4 to calculate the f prime of xi. So after the step 2, we will have our new approximation of the root, which is xi plus 1, and we had our previous root, which is xi. So in the step 3, we are going to calculate the approximate relative error using this formula. That means modulus of new value minus previous value divided by new value. Our new value is the current approximation of the current iteration, which is xi plus 1. Our old value or the previous value is the previous approximation of the root at the previous iteration, which is xi divided by the current value into 100. So that is the percent relative error that is going to be our criteria for terminating the code. So once this error is less than a pre-specified error limit epsilon s, we can terminate the calculation. We have already seen this step in our previous steps, and also if the error is greater than our limit, we recalculate from step 2. So this is how we apply the Newton-Raphson method in practice and in MATLAB codes or Python codes. So let's look at an example using Newton-Raphson method. For example, we are given this function e to the power minus x minus x. We have already seen this function in our previous lesson. That means whenever we are showing the simple iterative formula as an open method in the previous lesson, that is the same example that we are going to use, but rather here we are going to use the Newton-Raphson method instead of the simple iterative formula. So our initial guess is already given, which is x0 equal to 0. So this is given. So using this initial value, we start our calculation. So what we are going to do, we are going to find out the differential value of this function. That means f prime of x, which can be easily calculated. For example, e to the power minus x, which if we differentiate this value, this term, with respect to x, it is going to be minus e to the power minus x, and if we differentiate the last term x with respect to x, it is going to be 1. So this is a simple analytical approach that we can use in this example, but in practice there are many equations that we cannot use the analytical approach. For those cases, we are going to use the numerical methods. That means the central difference formula or forward difference formula or backward difference formula. But since we can calculate the true derivative formula with this example, we are going to use that. Okay. So for this case, we do not need to use the finite divided difference formula. But whenever you encounter any equation which cannot be differentiated so easily using the analytical forms, we have to use the finite divided difference formulas. So for now, we stick to the analytical approach. So in iteration 1, we are given the initial approximation of the root, which is xi equal to 0. We are going to find out the next iteration using the Newton-Raphson formula, which is xi minus f of xi divided by f prime of xi. Xi is 0. F of xi, that means f of 0, is going to be found out by replacing the x value with 0 in this equation. That means e to the power minus 0 minus 0. That means here. And where we are going to find out the f prime of xi, this is found from this analytical approach. Okay. So since we are given, we can easily calculate this differential form analytically. So we are going to use this form. But whenever you cannot find out the differential form of any equation, we are going to use the finite divided difference formulas. So if we replace these values, we are going to find out our next approximation of the root, which is 0.5. So if we calculate the approximate error, this is going to be 100% error. Okay. So it's because initially our initial assumption was 0, that's why it is 100% error. But let's see what happens if we go through the further iterations. In iteration 2, we are given the first initial approximation, which is 0.5. We got this value from the first iteration. Okay, this is the approximation of the root from the first iteration. So in iteration 2, we are going to use this value as our initial assumption. So if we calculate from the Newton-Raphson formula, we get the value of our new approximation of the root, which is 0.566311003. Okay, this is the new approximation in our iteration 2, and then we calculate the approximate relative percentage error, which turns out to be 11.709%. In first iteration it was 100%, but now see in iteration 2 it reduced to 11.709%. Still it is very high, so we need to calculate further. In iteration 3, we use the result of the second iteration as our approximation in the third iteration. And if we calculate through the Newton-Raphson method and the approximate relative error formula, we get an error of 0.147%. So the error is reduced much faster in this method, in this Newton-Raphson method. Initially it was 100%, in the iteration 2 it got to 11.709%, and in the third iteration it reduced to almost 0.1%. So if we want to find out better approximation of the true result, we need to use the further iterations, and we will see the true root of the equation is 0.5671429. So at the third iteration, we already got a result which is very much close to this true result. Okay, so Newton-Raphson method is faster than the simple iterative method and any other methods that we have so far calculated. So Newton-Raphson method is going to be our first choice among the methods that we have covered so far. So one thing I want to mention here is that Newton-Raphson formula can be derived from Taylor series formula. We already covered the Taylor series in our previous lessons, so try to derive it. It is as a homework and a new assignment. I would post it in our Books system. So try to derive the Newton-Raphson formula from the Taylor series. But Newton-Raphson formula has some limitations of its own. So let's find out some of the limitations that we are going to encounter practically there. For example, if we are given the function x to the power 10 minus 1 and we are given an initial guess of xi equal to 0.5, then it will take a lot of iterations to converge to a specific root. For example, in this case, it takes almost infinite iterations to get to the result of 1, because whenever the initial guess is 0.5, in the first iteration it is 0.5, in the second iteration it is going to be 51.65, in the third iteration 46.485, then 41, 37, 33. So this is a very slow procedure. That means the error is decreasing very slowly, and for these special cases the Newton-Raphson method takes a huge amount of time and computational resource to converge to a specific point. So that's one limitation of the Newton-Raphson method, that it fails in some special cases. Let's see some of other limitations of Newton-Raphson method. For example, look at this figure A. This is a special function. Okay, so let's assume we are initially given the point x0. Okay, so what we know about the basics of Newton-Raphson formula, that we need to draw a tangent to the curve at the point x0. So if we draw a tangent to the curve at the point x0, f of x0, then this tangent is going to intersect the x-axis at x1. Then we again draw another tangent at the point f of x1. Then that tangent point is going to intersect the point x-axis at x2. And once we got to the result x2, and if we calculate further, the next tangent line is going to intersect the x-axis at a very far point. Okay? That means the result is not converging, rather we go from x0 to x1 to x2 to a further point. That means the result is not converging to our original root. So for this special type of function, the Newton-Raphson method fails to converge to the original root. So let's look at another example. This is a function. Look at this. There is a value point at this region. So our initial starting point is x0. Okay. So if we want to draw a tangent at the f of x0 point, which results in x1 point, then we draw another tangent point to f of x1, which turns out to be x2 point. And if we calculate this further, we will see that at some point the tangent intersects the x-axis at a very far point, and that's where the method diverges. So Newton-Raphson method also fails to converge to the original root, which is situated here. So these special cases are there where the Newton-Raphson method fails to converge to the original root. Let's look at some other examples as well. Look at this. In this case, it is almost similar to a transcendental function. That means there are many roots of the function, here, 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 or here. So there are many roots possible, multiple roots problem here. So if we initially assume our initial guess to be x0, then we get our next iteration, the point to be x1, and then to x2. That means whether also, since there are many root points here, the function cannot converge to a specific root, rather it is diverging. So in this special case also Newton-Raphson method is failing. Okay, because the method is continuously diverging, it never converges to the true root. Similar to another example, look at this. In this function, and this function has no root. Okay, in this vicinity of this region. Also we are saying that there is no root because we are considering a small part of the function. There might be a root at further points which is not shown here. So let's say our initial guess was here x0. So at this point f of x0, if we draw a tangent curve, it is going to intersect the x-axis as x1. In the second iteration, we are going to draw a tangent point here, f of x1. But the problem is at this point, f of x1, if we draw a tangent, that is going to be completely horizontal with the x-axis. That means that tangent point is never going to intersect the x-axis at any point. If the tangent line is horizontal, that means its slope would be 0. If the slope is 0, that means in the Newton-Raphson formula, in the denominator there will be a 0 point. That means there is no result that we are going to find using the Newton-Raphson method. So all of these cases that we have shown here, figure A, B, C, and D, the Newton-Raphson method fails to converge to a specific root. And that's the problem. That's the specific types of problem that the Newton-Raphson method can encounter. So what we can say, there is no special type of or criteria to ensure the convergence of Newton-Raphson method. So what we can say is, if you see that at one point the Newton-Raphson method fails to converge, then stop the calculation and try out with a different starting point. It might happen that with the new starting point you might converge to a specific root. So we have to calculate further and further through iterations using different starting points. So what we have learned in these lessons, we have learned a new open method of finding roots of an equation, which is the Newton-Raphson method. And although there are some limitations of the Newton-Raphson method, it is still one of the most widely used root finding method. It is the most basic, at least most people try out this method at first to find out the root. Then if it fails, they try to go to the other advanced methods. We have also seen the algorithm that we use for the Newton-Raphson method. We have seen some of the limitations that the Newton-Raphson method might face, and we also seen that these limitations can be encountered if we start the calculations further and further. So please try out the MATLAB code that I have attached with this lesson. Newton-Raphson method is very important, so try to understand this method in the MATLAB code line by line. So try to avoid the unavoidable limitations of the Newton-Raphson method by changing the initial starting points. So try to apply the code at various types of functions, both algebraic functions and transcendental functions. So I am giving you the code, MATLAB code, so please try out that. So in the next lesson, we are going to find out a more advanced method of the Newton-Raphson method, which is known as second method. This second method is, we will see that it is not an entirely new approach, rather a modification of the Newton-Raphson method. So we are going to try out that second method in our next lesson. So till then, thank you so much.